Okay, so in chapter 3, we're going to look at the problem of optimization. Optimization crops up a lot in statistical contexts. In particular, many estimation problems of one form or another can be set up as optimization problems. So typically, these sorts of problems are set up as minimization problems. All right, so you would say I've got a function f, which is a function of theta, and I want to find the theta that makes f as small as possible. So we're typically thinking of f as being a scalar-valued function of some vector valued quantity theta. Now, in statistics, we very often want to maximize things. Yeah, so we might want to maximize a likelihood, a log likelihood, find a posterior mode, etc. So very often we want to maximize a function f, but in fact it's the same problem, you just flip the sign. Yeah, so maximizing f is the same as minimizing minus f, so it's really not a big deal, although it does sometimes cause confusion and slightly mysterious bugs in code, etc. But traditionally in the optimization literature, everything is set up as a minimization problem, and so if you want to maximize it, you just flip the sign. So some examples we've hinted at there. You might, in the simplest case, we've already seen, you might want to minimize a cost of some sort, like a least squares penalty. So you might want to find a least squares estimate. More generally, you might want to formulate the problem in likelihood terms. And so in that case, you would want to maximize a log likelihood or minimize a negative log likelihood, which in certain cases might look a lot like a least squares cost function, but certainly not always. In the Bayesian setting, we might want to find a posterior mode, etc. Okay, so lots of problems in statistics, especially estimation style problems, can very often be set up as optimization problems. So we're going to take that as read now. So we have a function f, it's a scalar valued function, and we want to minimize it. And so we should think of f in this context then as being some sort of cost or penalty. Yeah. So just thinking actually about the least squares penalty type problem is a good thing to have in your head. All right. So we're minimizing some cost function by trying to find the theta that makes f as small as possible. Okay. So theta, is something that we can vary to try and find a minimum, so it must take its values from some set. So we use capital theta to denote that kind of set of all values that theta can take. But the whole idea of especially numerical optimization, which is what we're going to be mainly concerned with here, it really makes some assumptions to make this problem tractable at all, right? So the first thing it assumes is that, if we come up with some idea of a theta that might be good, then we can actually evaluate the function at that value of theta. Yeah, so at least, obviously subject to computational constraints, we can potentially evaluate f for any particular theta that we're interested in, right? So that's kind of taken as read, and I don't think that's, sometimes it's an assumption, but very often that's not such a big deal. But the more subtle one is that in order to have any hope of finding a theta that minimizes the function, we need to be able to sort of vary theta and see what's happening and see, are we going uphill or downhill? Are we getting closer to a minimum or further away from a minimum? And to do that, you really need some sort of notion of how close two different elements of theta are, and some sort of vague notion of continuity. I don't mean continuity in the strict mathematical sense, but I mean some sort of notion that if your values of theta are close together, then your values of f are going to be at least reasonably close together, at least on average most of the time. Yeah, so that's not to say you couldn't ever have any jumps in your function, but it's going to be very hard to find a theta that minimizes a function if your theta space is vast and there's essentially no structure that allows you to navigate in a sensible way, right? It's going to be more or less impossible. Yeah. So these two assumptions are going to be sort of underpinning pretty much everything we do. They're going to be quite reasonable in the context we're going to be looking at, because we're mainly going to be thinking about some continuous space, capital theta, and some smoothly varying functions f. So both of those assumptions are going to be broadly true for the problems we're considering, but you can actually imagine situations where it's not true. And particularly if theta is a discrete space, it really can sometimes be the case that it's pretty hopeless trying to navigate that space in any kind of systematic way, because you just don't have this kind of notion of closeness and continuity that you have in the continuous case typically. Yeah, so discrete optimization problems we're not going to worry about. I mean, there are classic problems that you've probably heard of, like the traveling salesman problem, and these are just very hard. But it's the discreteness that makes them hard. So we're going to just stick to continuous theta, because we're typically thinking about statistical problems where we're varying continuous parameters to try and maximize a likelihood or whatever. And so if we can at least have a reasonable way of tackling these continuous problems, we're going to at least have a nice broad class of problems that we can do something sensible with. Okay, so when we're thinking about minimizing a function, there are two sorts of minimums that we might be interested in that is important to distinguish between. So typically, what we can hope to do is find a local minimum of f, right? So that is a point, theta star, such that for any point sufficiently close to theta star, the function will be not smaller. Yeah, so it's a local minimum in that there's some notion of closeness to theta star, and that we're only asserting the optimality of our theta star in the vicinity of theta star, subject to this notion of closeness. So you see how this notion of closeness is really important. So that's what we mean by a local minimum. And so you're thinking about, just a little dip in the surface, right? That if you rolled a ball, it would go to the bottom of that hill, and that would be your local minimum. But there's not saying that there isn't some other well that you could have found further away, where if only you'd known about it and you'd rolled the ball down the hill, starting much closer to that other mode, then other optimum, you wouldn't have found that other optimum. That's not the case. But typically, we're navigating this theta space locally, and the best we could hope to do really is find a local minimum of f. Okay, so a global minimum would be a theta star such that for any perturbation, however large or small, there was nothing better. Yeah, so that's really typically what we'd like to know, right? So typically we'd like the global minimum, but that's a very hard thing to find in general, and so we generally develop methods that find local minima and then have heuristics on top for whether or not they're global. So for example, we could just run the algorithm from lots of different starting points. Each of those algorithms would find a local minimum, and we'd hope that the minimum of those local minimums might actually be the global minimum. But again, in general, there'll be no guarantee of that. The classic exception that does actually crop up quite a lot in statistical context is the case of a convex function. So sometimes the thing you have to optimize is a convex function, and occasionally you can even prove that the thing you have to optimize is a convex function. And if you can prove that it's a convex function, then actually you do know that if you find a local minimum, it is a global minimum. Okay, so that we're not going to focus on that here particularly, but it is definitely worth knowing that if your function is convex, then local minima are global minima. But in fact, there are special optimization techniques that can exploit the convexity as well that we're not particularly going to talk about here. So the kinds of optimization methods that we are talking about here are typically myopic in this sense, that they look around where they are now. You're currently at theta. How can I figure out where to go next? Well, I figure out where to go next on the basis of what I already know about the function in the vicinity of where I am, essentially. Okay, so we know the current best guess, and we use some feature of the current best guess, or things we can evaluate about the current best guess, or maybe some previous recent points, and use those in order to say something about where to head next. Okay, they don't typically have a global overview of what the function looks like. I mean, there are optimization methods which do a slightly better job of that, but we're not looking at those here. So how on earth do you tackle this problem? Well, especially if the problem isn't too high dimensional, it can be really useful to try and look at the thing you're trying to optimize, at least in some way. Now, unless the parameter space that you're working with is 1 or 2 dimensional, right, you're not going to be able to do this perfectly, right, because we're not very good at visualizing high dimensional spaces. But typically we can look at slices, 1 or 2D slices, through the thing that you're trying to optimize, in order to try and get some intuition for what the surface looks like, how well behaved it is or badly behaved it is, or how whether it has multiple modes, whether it is a smoothly varying surface or a rough surface, those sorts of things. So very often, by looking at 1 or 2D slices, you can get a little bit of intuition for what it is that you're dealing with, and that can be very, very useful for optimization purposes. Right, so let's have a look at an example. So here we're just going to assume a simple least squares type problem. So we said it can be useful when thinking about minimizing something to have in mind a least squares minimization type problem. So let's set up a least squares minimization problem, but we're going to do it for this nonlinear dynamical system. Okay, so we've got a little dynamical model here. For those of you who know about such things, it's just the logistic map, but it gives us a way of computing an nt plus 1 from an nt. So that defines, together with an initial condition, the time evolution of this system. But because there is a quadratic term in, it's nonlinear and it has some interesting behavior. So we're going to suppose that we've got some noisy observations, right? So this is going to make it a sort of a more statistical problem. So there is this true dynamical system, but we don't observe the true dynamical system perfectly. We observe noisy observations of the true dynamical system, subject to some Gaussian noise. Okay, so that's going to give us a least squares type likelihood. So we could just go for least squares, but it's essentially the same as maximum likelihood in this case. We're going to minimize the the difference between our inferred behavior of the dynamical systems and the observations we have on that system. And so given that there were parameters in this model, okay, so the potentially a few different parameters. So there's potentially the starting point, there's the growth rate R, and there's the so-called carrying capacity K. So all of those are potentially parameters we could be interested in. So let's just think about R and K. So our time course behavior is a function of both R and K, and so we might ask the question, what values of R and K are most consistent with the data that we've observed? And one way of answering that question might be to say simply, find the R and K that minimize the least squares error. Right, so to investigate this problem, let's just simulate some data. So we simulate with known N, K, and there's the sigma as well, which is the noise. And we could pick an R, but let's pick a few different R to understand the behavior and how the behavior of the model changes for different values of the growth rate R. Okay, so in the first case, we're going to simulate the data with R equals 2 and the other parameters as previously described. But then we're going to pretend that we don't know R or K and try and estimate them from data. So what could we do? Well, we could look at some transects. So on the top, we've got on the top left here, we've just got the actual data. Okay, so it's just, the time course evolution of this dynamical system. And the question is, well, what values of R and K does that correspond to? Well, what you could do is you could fix K. Okay, so the question is, what do you fix K to? So here we know the true K, so we could even just fix it to the true K. But then look at how that least squares cost function varies as you vary R. And you see that it's got a nice minimum at around about 2, which is good because that was the value used to simulate the data. So you see that everything is working quite nicely here, at least if we fix K to the value that was used to simulate the data. When we look at the function, the cost function as a function of R, it's nice and smoothly varying and has a minimum, a nice well-defined minimum at around about the true value that was used to generate the data. So that is all great. Okay. Now let's look at what happens for different growth rates. So if instead of simulating data with R of 2, we simulate the data with an R of 3.2, then we're going to, again, pretend that all we have is the data and we want to estimate R and K from it. How do we get on in this case? Well, in this case, things are not so straightforward. The data we see looks a bit different. It's got this oscillatory behavior. But more importantly, when we look at the cost function as a function of R, we see that it's not so nicely behaved this time. It's not a nice smooth function, at least when we get to, R values above about, 3.6, 3.7. Okay, the cost function becomes very irregular. Now, fortunately, our mode or our minimum value is around about 3.2, which is good, right? So if we set off our optimization procedure for any value smaller than, say, 3.5, then actually there'd be a good hope that if we sort of headed downhill in a sensible way, we would find that optimum at around about 3.2. So it's not terrible. But you can see that if we'd happened to initialize our search at a value up closer to 4, then we might have had real trouble, right? Because that surface is then very rough. It's not clear which is uphill and which is downhill, and there's no kind of smoothness that we can exploit. So we're starting to see that that function is maybe not so nice and maybe not so easy to optimize. And so finally, with data at 3.8, so simulated data with an R of 3.8, you can see that there is a minimum at around about, well, it's actually a bit less than 3.8. It's actually more like 3.7. But anyway, that's not the point. The point is that in the vicinity of that optimum, the function is not smooth at all. Right? It's a very rough function. And so that's going to be a very, very difficult thing to optimize. Right? You can see that if you initialized your search maybe say at a value of R equals 2, you'd probably find a local minimum at around about 3. Okay, and that would be a perfectly reasonable thing to think was a global minimum, right? It's clearly a local minimum. It's clearly a minimum in quite a broad vicinity of the value 3. The function is quite smooth in that vicinity. So if you didn't think to look at values bigger than 3.5, you'd be pretty happy that you'd found at least a local minimum and probably a global minimum. But in fact, you see that if you search values bigger than about 3.6, 3.7, it all turns into a bit of a mess, right? So this function is really not very nice at all. But if you think about the definition of this function, it was an incredibly simple thing, right? It was just a least squares for a very simple nonlinear model. So even, and this is the point, that even very simple systems can give rise to cost functions that seem very, very innocuous, but actually have very, very difficult behavior. And so this is, this is not a nice problem when we're dealing with R in this sort of range. So that illustrates the fact that not all functions are nice, which is useful, and that we got some useful information about that by looking at the transects. But it's not always that easy. So here there were only two parameters, and so we could have actually done some surface. Okay, so let's have a look at the surface. So we could do that here, right? We can look at R and K and see what's going on. But in general, for high dimensional functions, you can't. So you might hope that by looking at 1 and 2D slices through your function, you can get some insight into its behavior, but that's not always the case. Okay, and so that's just something to be aware of. You can sometimes be misled. Okay, so for example, here's a 1D slice through a 2D function, which looks pretty horrible because it looks like it's got lots of local modes, but actually if only you knew what the real surface looked like, that surface actually only has one local minima, and in fact you can find it from any starting point. So any kind of downhill method will find the one local optima from any starting point. So in fact it could hardly be a better function in some sense, but looking at a 1D transect gave you a poor impression. And the opposite problem can also happen. You can look at a couple of different transects through another 2D function, right? So an X transect and a Y transect, and see they're both nice and unimodal. So again, this is the problem with statistics, that this is now a likelihood function, and this is something we're wanting to maximize. So if we're thinking about minimization, we should really turn it upside down, but let's just leave it this way up because we're used to looking at likelihoods this way up. So we're now thinking about maximization, and so we think, well, there's a nice simple mode in both the X and the Y directions, so that's obviously a nice simple function. We should have no problem just maximizing that. But in fact, the real function has three modes in it, three maxima, and if you find one, that's great, but you don't know it's the global one. Okay, so if you find the global one, then great, you were lucky. But if you don't, you're probably not going to know about it. There's not much clue that you've missed another mode. Okay, so it's worth doing this, right? It's worth looking at 1 and 2D slices through your function and looking at a bunch of different slices and trying to get a bit of a feel for what's going on. But it's not perfect, and that's just how it is. Okay, so we've talked a bit in generality about how to think about optimization, but let's now think about how to actually formulate some algorithms, in particular some algorithms that sort of head downhill in some appropriate sense. So how do they work? So typically you start with a guess, okay, and the better the guess the better, but we start with a guess, so that's going to be our initial theta naught. And most methods do sort of something like the following. They probably are going to evaluate f at your current theta, right? You're probably going to want to know that. You may also want to know first derivatives of the function at that particular value of theta. You might even want to know second derivatives at that particular value of theta, though whether or not that's practical will depend very much on the function. Okay, so you're going to want to know something about f at the particular theta you have right now, and you can see why gradient information in particular might be very useful, because that will tell you which way is down. Okay, so lots of methods make use of gradient information. So now what do you do, given that you've got some information about f? Well, you're going to use that information to probably define a search direction. Okay, and so that might be downhill, or it might be something a bit more subtle than that. And then what you're going to do is you're going to move in that direction. Now, the thing we're not really going to talk about very much in the context of this course are very smart ways to choose how far to move in that direction, right? So you can imagine that could be quite important, but we're not going to spend a huge amount of time thinking about it. But once you've picked a direction, you then have to decide how far to move in that direction. So we could call that alpha, and then we could either do what's called a line search to find the value of alpha that minimizes the function in that direction. If your function is cheap to evaluate, that's probably a good strategy. So just keep varying alpha and do like a 1D minimization in order to find the alpha that minimizes your function as much as possible in that direction, right? So that could be a good strategy. Or there are other heuristics you could do, right? But you're going to move in the direction that you know is downhill, and then you're going to update your theta to that new value that you found, and then you're going to go through the loop again. So your best guess is now better than your previous best guess, and you're going to start again. Yeah. So that's how a lot of iterative optimization methods work. It's not how every optimization methods work, but it's how essentially all of the methods we're going to think about work. Now, there's a sort of slight variation on this that is really not so different at all, and that is to say, well, rather than just picking a search direction and heading downhill or heading in that direction, I'm instead going to build a model of what that surface looks like in the vicinity of my current best guess, and I'm going to use that model to decide on where I should jump to next, potentially as the minimum value of that locally defined model. Now, although that sounds very different, the way it's being presented here, actually they're more or less the same thing. Okay, so it's worth making the distinction because there's a distinction in the literature. So methods of type A, where you just pick a search direction and move in that direction, are called search direction methods, and methods employing the approach B, based on some sort of local model, have the slightly confusing name trust region methods. Okay, but in fact the distinction between them is really very small, because you're always using some kind of model to decide what might be a good direction to go in anyway. Yeah, so there isn't really a huge distinction between them, but we'll start with search direction methods and take it from there. So how are we going to tackle this problem of thinking about where to go next? Well, the way we're going to do it is we're going to use information that we know about the function where we are now. And the kind of main mathematical trick we have for using local information to say something a little bit more global is really Taylor's theorem. Okay, so for a multivariate, a scalar-valued multivariate function, this is what Taylor's theorem might look like. So this is one way of presenting Taylor's theorem. So in case you haven't seen Taylor's theorem presented this way before, let's just talk through it. So we're interested in expanding a function about a known point theta, and we're going to make some perturbation of that known point theta, and we want to know what the function looks like for this perturbation. So we're expanding around theta, so we start with f of theta and then we perturb it. We perturb it with a term that's linear in the perturbation and determined by the gradient, and then a term that is a quadratic form in the perturbation that is determined by the Hessian matrix. Okay, now Taylor's theorem can be presented in lots of different ways. So if you're familiar with at least the real case, the function of a real valued function of a real input variable, which is the version you typically meet first, you'll know that Taylor's series is an infinite series. Taylor's polynomial is some finite truncation of that infinite series. And what Taylor's theorem does is tell you how Taylor's polynomial relates to the true function by introducing some error term that tells you, what the error is associated with that truncation of the Taylor series. Yeah. So here, what we've done is we've written it out to first order. So our Taylor polynomial is just f theta plus this gradient term, and then this second term here is the error term associated with that first order approximation, and it's written in Lagrange's form. So if you recall from your kind of real analysis courses that you can write the error for Taylor's theorem in various different ways. So this is written in Lagrange's form, and so this is a first order Taylor series approximation plus a second order error term. Okay, and so this is exact equality here. This isn't approximate at this stage. There are various ways we can make it approximate. So we could make it approximate by ignoring the second term, which would then just give us a first order approximation. Or we could make it a second order approximation by putting t equal to 0 in this Hessian here. Okay, so if we just evaluate the Hessian at theta, then we get a second order approximation. So both of those will be approximate. The second typically more accurate than the first, but the way we've written it here is an exact equality, and it gives us both of those approximations quite easily. So that's quite a convenient way of writing it. Okay, so yeah, we're going to use the gradient and the Hessian potentially. And yeah, so how would we know if we had found a minimum? Well, so this tells us how to know if we'd found a minimum. If we found a minimum, then presumably the gradient is going to be 0, right? Because otherwise there'd be a downhill direction. And hopefully we'd also find that the Hessian is at least positive semi-definite, ideally positive definite, because that would tell us we had a nice minimum. Yeah, so that's how we know if we've found a minimum. So we're looking to make the gradient 0 at the very least. Okay, I've said that. Right, so what's the simplest thing you could do? The simplest thing you could do is gradient descent or steepest descent. So what do you do in gradient descent? Well, in gradient descent, you just rely on the first order Taylor approximation. And so you take your guess, theta k, and say, how can I go downhill as fast as possible? And you go downhill as fast as possible by going in the steepest direction down. How do you find the steepest direction down? Well, the gradient tells you the steepest direction up, so minus that is the steepest direction down. Okay, so we know from our first order approximation, Taylor's theorem, that fk looks like this, and it's pretty clear that if we put delta parallel to minus the gradient, okay, so you make delta proportional to minus the gradient, then that's going to be the steepest hunt downhill. And so just to make that precise, if we just normalize by the gradient, so we just get the direction of length 1 delta, and say, okay, what happens if I now move in that direction for alpha bigger than 0, obviously? Well, if we plug that into our first order Taylor's theorem, what we find is we get this inner product here, which gives us the norm squared. So we cancel the norm on the bottom, and we just get that we're going downhill, right? We know we're going downhill because we know this norm is non-negative. In fact, we know it's positive. And so this alpha here that we know is positive, we know is taking us downhill. Yeah, and in fact, it's pretty clear. You can, do the inequalities that any other direction will take you downhill less fast than minus the gradient. Yeah, so moving in the direction minus the gradient is going to take you downhill as fast as possible. Whether that's a good idea or not is a rather subtle question, but that's what steepest descent does. Okay, so we've now got this question of how far we move, how to choose alpha. And like I said, we're not going to spend a huge amount of time and effort looking at that, but essentially we don't want to spend ages deciding on the absolute best alpha, especially if the function is very expensive to evaluate. We don't want to be evaluating the function in lots of places. And so we just have some heuristic for moving a particular direction, and if that doesn't take us downhill, then we just halve it and halve it again, say, until we get a move downhill. And we know if we halve it enough, we'll definitely get a move downhill, right? The problem is if you go too far, you might start going uphill again, right? That's the issue. But you know that you're starting off going downhill. So if you choose a jump that's too big and it actually takes you uphill, if you just keep halving, you will eventually move downhill. You might not move downhill very far, right? That's the trade-off. But that's a nice simple search strategy. Yeah, you just try a jump. If it's too big, you halve it until you're going downhill, and then you use that. So there's this function that you should in fact be familiar with from the preliminary material called the Rosenbrock function, and we can look at what happens when we run steepest descent on this function. well, it works. It just heads downhill, and this function turns out to have, a global mode, and so you just head downhill to find the global minimum, and it works, but it takes a long time. It takes a lot of steps. So in fact, here it took nearly 15,000 steps, right? Which is it okay? Is it ever okay? It would be okay if your function was very cheap to evaluate, but if your function was expensive to evaluate, this would be a massive problem. And this is very commonly a problem with steepest descent, because although intuitively heading downhill as quickly as possible sounds like a good strategy, there are actually lots of problems with that. And so in fact, there are smarter things you can do in general than just head downhill as steeply as possible. So why might that not be such a smart thing to do? Well, one issue mentioned here is the fact that there is scale dependence, right? So if you rescale one of your axes, you stretch an X or a Z or something, that doesn't change whether the mode is, if you rescale that correspondingly, but actually it does change all of the steepest descent directions, and so it does change the behavior of the algorithm. So the fact that the algorithm changes depending on how you scale your function is kind of one indication that actually there's more to optimization than just heading downhill, right? So what downhill means depends on how you've scaled your coordinates, and that doesn't seem ideal. So Newton's method doesn't have that flaw. So Newton's method is scale invariant. So what is Newton's method? Well, Newton's method, instead of just working with the first derivative, the gradient, it brings in the Hessian information as well. So it uses a second order approximation, and intuitively that's why it's better, right? So the steepest descent is basically what you do if you only have the first order approximation, you only have gradient information, whereas Newton's method is the method you use when you have second order gradient information as well, the Hessian information, because that allows you to make a quadratic approximation, and a quadratic approximation is typically going to be much better than a linear approximation. And in particular, a quadratic approximation also will have a minimum, and so as well as getting information about what direction to head in, you've also got information about how far to head in that direction, because if you build your quadratic approximation, you can jump straight to the minimum of that quadratic approximation, and that is going to get you to your answer much faster than just hopefully heading downhill. All right, so let's start then from Taylor's theorem, but we'll use the second order Taylor's theorem that includes the Hessian term. So that is then a quadratic approximation to our function f. The right hand side is quadratic in delta. That's our quadratic approximation of our function f. It has a minimum. So what's its minimum? So there are two obvious ways you could find the minimum. One is you could complete the square on this thing. That's a little bit fiddly, but you can totally complete the square to find the minimum directly without any vector calculus. Conceptually, or at least mechanistically, it's easier just to differentiate and equate to zero. So if you know your vector calculus, and again, that matrix cookbook I referred to earlier is handy for this sort of thing as well. But you differentiate with respect to delta. So that's differentiating with respect to a vector. So it's really like evaluating the gradient of the function. But anyway, if you differentiate with respect to delta and set to zero, then you get this equation here. So this one. So just to be clear, this one drops out, this constant term. This one differentiates to give you your fk here, and this quadratic differentiates to give you, well, twice this times delta, but the twice cancels with a half, so you just get this term here. So that's where this comes from. So this term gives you this term, and this term gives you this term. Okay, so you differentiate and equate to zero, you get that equation there. So just to be clear, this Hessian here is a matrix. And so to find delta, which is the thing we're interested in, we need to pre-multiply both sides by the inverse, or rather solve this linear system. Okay, so we're back to solving a linear system. Right? So matrix computations are back again. We're going to solve this linear system. This is sometimes a positive definite matrix, and we've seen how to solve linear systems involving positive definite matrices already. Okay, so that's basically Newton's method. We just use this equation here to jump to the next k and then go through the whole process again. So as long as we can easily get gradients and Hessians, this is actually very, very simple and works very, very well. All right. The question is, can we easily get gradients and Hessians? So crucially, as I've already mentioned, it suggests not only the search direction, but also the step length. Okay. Now, because that quadratic approximation isn't really exactly true, it could be that when you evaluate the Newton step and check the value of your function at that newly proposed value, although you are expecting it to have a smaller value than the value you started from, actually it doesn't. Okay, so that can happen, especially if you start a long way away from the minimum. So what do you do in that case? Well, in that case, you can just keep halving the step length until you do find that it does take you downhill, and then you accept that. And it turns out that except in like incredibly pathological cases, if you halve enough, you will end up going downhill. Of course, you'll end up making a very modest jump, and that might not be, good, but you will end up going downhill, right? Your local approximation is roughly right in the vicinity of your function, and so if you keep halving your step length, you will end up going downhill. Particularly if you make sure your Hessian is positive definite. Okay, so that's the other potential issue with Newton's method, is that we have to be able to solve that linear system, and to do that we really require that this Hessian is positive definite. But there's no guarantee that a Hessian is positive definite, right? If you have a nice well-behaved local minimum, then it will be. But if you're miles away and your function is very complicated, there's no guarantee that the Hessian that you evaluate where you are now will be positive definite. Okay, so that is potentially a bit of a problem with this method. However, it turns out that it's much less of a problem than you might fear, because we're essentially solving this linear system here, where H is the Hessian. But if we think about, well, what if H wasn't the Hessian? Actually, what if it was just some arbitrary positive definite matrix H? Would this be a downhill direction? And the answer is it would. So as long as H is positive definite, if we solve this linear system, we get a direction that is definitely a descent direction. That's simply using the positive definiteness of H. So to see that, you just say, okay, well, put our search direction as the solution of this linear system, and let's see what we get. And what we get is we're going to search in the direction delta, but we're only going to move an amount alpha. And if we do that, we just substitute in for delta. What we find is that because of the positive definiteness of H, H inverse is also positive definite, and so this is guaranteed to be positive. And so as long as you choose alpha small enough, you're definitely going to go downhill. Yeah, and so whatever positive definite matrix H you use here, you are always going to get a downhill search direction, which is why this halving the step length thing is guaranteed to work, as long as you make sure your Hessian is positive definite. So what this means is that if your Hessian isn't positive definite, if you could just modify it in a minimal way to make it positive definite, then you get a matrix here, H, that is very similar to the Hessian, but just slightly nudged so that it's actually positive definite. You're going to get a sort of a compromise between the Newton solution and a downhill search direction, right? Which is probably a good compromise. So how do you do that? Well, we just somehow need to modify the Hessian to make sure it's positive definite. So it's always going to be a real symmetric matrix, right? So you're always going to be able to form a symmetric eigen decomposition of it, at least if the dimension isn't too huge. So what you could do there is just reverse the sign of any negative eigenvalues, replace any zero eigenvalues with a small positive number, and that's it, right? Then you recompose it back with its orthogonal matrices, and you've got a Hessian that's very like the one that you started with, but is now positive definite. You can actually do things much cheaper than that. So, for example, if it's you've got a big matrix and it's going to be very expensive to do this symmetric eigen decomposition, well, you can just add something to the diagonal, right? So if you add the identity or some multiple of the identity to the diagonal of that Hessian, eventually you will make it positive definite. Yeah, if you add enough to the diagonal, you will make it positive definite. And that's kind of an interesting choice, a multiple of the identity, because if you go back to the this equation here, if you choose H to be the identity, then you just have steepest descent. Yeah. So what you're doing when you add a multiple of the identity to your Hessian is you're sort of nudging your search direction from the true Newton search direction, which is directly towards the minimum of the quadratic approximation, and you're nudging it in the direction of steepest descent. And that's usually a fairly safe thing to do. So one way or another, you just make sure that your Hessian is positive definite by modifying it in as minimal a way as is practical to make sure it's positive definite, and then you solve the linear system and off you go. And that's kind of guaranteed to work in some sense. Okay, so putting all of that together, we can now write this out in the form of a nice kind of simple, clear algorithm for how to do Newton's method in practice. So we start at k equals 0 with a guess, theta 0. We need to be able to evaluate f and the gradient of f and the Hessian of f at that current value, theta, which we're now going to call theta k. That's going to give us our quadratic approximation. We can look at the gradient and the Hessian to decide if we've already found the minimum, because if we have, we can terminate. If not, we need to worry a little bit about whether or not the Hessian is positive definite. And if it's not, we should perturb it so that it is, and that's going to give us a modified quadratic model, but it's going to be similar to the quadratic model that we got directly from Taylor's theorem. So now we can solve for our search direction. So this now represents our potentially slightly modified Hessian, but hopefully not modified very much. So we just solve this linear system using the most efficient method we have to hand. And of course, if we've already got the eigen decomposition of it, because we've used it at this step, then in fact, we might use the eigen decomposition here in order to solve this. But one way or another, we can solve this linear system to get our delta, and we can either jump straight to that newly suggested value, or we can check to see whether it really does take us downhill, and if it doesn't, we can just successively halve the distance that we jump until we do go downhill, so thereby ensuring that we at least always go downhill. Yeah. And we know that that will work because we know that if we've got a positive definite matrix, then we definitely have a downhill search direction. So we know if we halve delta sufficiently often, we will definitely go downhill. There's no question about that. Okay, and that's essentially it. We update our theta appropriately and we go around the loop again. So that's essentially it for Newton's method. So how well does it work? Well, if you apply it to that same function we've just done steepest descent on, where it took 15,000 steps, Newton's method converged in 20 steps, which I hope you'll agree is a massive difference. It has the additional cost that you need to evaluate the Hessian at each step, right? So it doesn't come for free, but the difference between 20 steps and 15,000 steps is going to, allow you to pay quite a heavy price to get the Hessian before you worry about that. Yeah, so Newton's method is really pretty impressive in many cases, and there isn't an attempt at a figure here, but it's not rotated properly in here. No, let's. Can I rotate it? Yeah. Yeah, so you still can't see this very well because it's clipped, but the idea is we're now reading across left to right for the different iterations. So this is after 2 iterations, and then the third iteration. And the idea is if you study these contours very closely, and you're better off studying them closely in the PDF of the notes that you have, what it's showing you, as well as the contours of the function you're trying to optimize, it's also trying to show you the contours of your local quadratic approximation at each stage, so you can see where it's jumping and why. But essentially, it just jumps very quickly and efficiently along the function until it finds the minimum in an impressively short number of steps, despite the fact that this is really quite a non-trivial function that you're trying to optimize. Right, this is deliberately chosen as being non-trivial to navigate your way around. It's quite non-linear, but Newton's method deals with it surprisingly well. And so I think this is a good place to break.